thank the speaker again. And the next speaker in this section will be Juliana Vizzotto of the University of Brazil. And she will be speaking on parallel quantum computing.
Okay, so thank you. This work is in collaboration with Robert Dubois, and so we're talking about modeling parallel quantum computing using transactional memory. So, first of all, this talk is about how we can see this quantum computing approach from the programming point of view. Okay, so the quantum computing approach we are considering here is the ensemble quantum computing. Actually, parallel quantum computing using the ensemble quantum computing. So we are trying to show how we can see this model for quantum computing from a programming point of view. And we use for this software transactional memory, which is a model to programming parallel concurrent programs in a multi-threaded environment with shared memory. And that's very, it's a new approach to these multi-core architectures. And then we will try to show how this parallel quantum computing in a single ensemble can be programming use STM, software transactional memory. Actually, it's transactional memory, and software comes from, we are using Haskell, the functional language Haskell to show. So the packaging Haskell is software transactional memory. And we are trying to see this in a bigger context. How we can see this programming point of view from parallel quantum computing in a single ensemble in a quantum programming language. So, first of all, let's just see a bit about ensemble quantum computing. So, quantum computing, we can operate in parallel or in our input at once, and the amount of information that can be extracted from a quantum system is limited, and the measure is a irreversible operation. So, what is different? What is different in ensemble quantum computing? Basically, the difference is the measuring operation, and that is we use many copies of a quantum system, and we use this average measurement, the expectation value, to obtain the result, the classical information, and is realized in a macroscopic way by nuclear magnetic resonance spectroscopy. So let's see. Basically, we can consider that we have a number of molecules which are working in parallel. And our molecules are doing the same computation, are solving the same problem. And so to obtain the result, we use this expectation value, the measure of the expectation value to obtain the result. And so it's like a quantum parallelism at molecular level and classical parallelism at macroscopic level to obtain the result. And there is, it's not doing, the molecules are working parallel, but they are solving the same problem. So what is parallel quantum computing in an ensemble quantum computing? This is a work by Long and Xiao. And they try to see that ensemble quantum computing to solve problems in parallel, quantum problems in parallel, and to speed up some quantum algorithms. So the idea is that we have the the ensemble of molecules, and the molecules are working in parallel to solve a problem, but it's like a classical parallelism. We can distribute the work between the molecules. So we can, if we consider a system with 21 molecules, the parallel quantum computer in a single ensemble works in a state divided in two parts. The first part is like if we are working in parallel, we have process. So the first part is with respect of process, and the second part is with respect of the state of the process. So I will show you in more details in the next slide. Then, so we have in this parallel model, I state like this, a mixed state. This is a density operator, and we have a distribution N1, which respect with each molecule, and N2, which respect the state of each molecule. So a unitary transformation in this state is like N1 is with we have any molecule is a process. Then N1 is the identification of the process, and this N2 distribution is the state, which can be in a superposition. So and a unitary transformation in this parallel computer, which works in quantum parallelism in this N2 register, and in classical parallelism in this N1 register, can be described by these operations. It's a state which transforms all the state. It's like this is a global state. We have a global state. So the idea is that there are N1 computers working in parallel, and the computation can be the same for all molecules. But the database, the numbers which are represented by different molecules can be different. So this can speed up some quantum algorithms like Groover, sorted search database, and SHARP. So this is the parallel model which we want to see in a programming point of view. So this is clear. It's clear that we have here this. We have a global shared state between all this process, all these molecules, and so we can see this as a multi-thread environment. It's like a process that are working in parallel and share some memory. And STM is a mechanism for synchronization, which is used in classical computing, traditional computing, for synchronization of concurrent processes which share memory. Then the idea is to have a high-level approach to make parallel programs. That's hard to synchronize parallel programs which share memory. And the idea is to have a high-level way to do that. And so STM is very simple, and the idea is the same as a database translation. And I will show here the idea in the context of the programming language Haskell, the functional programming language Haskell. Then the idea is that programmers define an atomic block that are executed atomically with respect to any other atomic block in the program. So in Haskell, we have a primitive atomically, which is of type STM-A. A is any type in the language, and which just returns an IO, an input-output. Then this is in Haskell and in any programming language. This is important because of this is the type system which can I will show which can take some tasks for us. Then the idea is that a memory transaction is only committed only if no other transaction has modified the memory. if there was concurrent access to shared variables, the transaction is restarted. It's like a process is, the abstraction is that a process is working as if the piece of memory is dead. Then an execution of atomically block must guarantee atomicity. Then the effects of atomically block are visible at once, like a database transaction. And isolation. The execute of atomically block cannot be affected by the execution of other threads. If this happens, then the execution is aborted. And so just the idea is that the programmer just define the block which needs synchronization as atomically, and then it is only executed if there is no other process accessing the same part of the memory. In contrary case, the block is aborted and restarted. And then in Haskell, inside a memory transaction, we have transactional variables. It's like it's monadic is side effect in the context of a pure functional language, and so we can write in transactional variables, and we can read. It's just some of the actions we can do, read and write. So we can have a variable which have a value of type A, and we can do an STM action in this value. And to write in a transactional variable, we can use the value of type A and do some action in it. Then the type system must guarantee that the only actions that are executed inside the block are or a pure or STM variable. There are no I/O actions inside the block. So how we can do this? How we can see that parallel ensemble quantum computing using STM? We use our work in which we have superoperators as arrows. We have modeled superoperators in Haskell using the concept of arrows, which is a generalization of monads. And then we propose to use inside the transactional variables density matrices. That is that global state here. It's a density matrix inside a transactional variable. And then we can define global computations in this transactional variable, use the superoperators, which we have defined before. So the use of the goal of using STM is to synchronize the access of critical parts of the states. In quantum computation, mainly when we are doing operations like measurements. So, okay, so this is just an example, and I don't have time to show. And so it's just how we can program a process which is assessing this global state. And then we can program a lot of process, in a multi-thread environment with a global quantum state shared. And so how we can see this in a bigger context, there is this new work by Lindley, Wadler, and Isle about the arrow calculus, which is a calculus version of the categorical concept of arrows. And it's very simple and very elegant, and just augment simple tuple lambda calculus with 4 constructs satisfying 5 laws. And we have just to give it work, which is the arrow calculus as a quantum programming language. We just use the translation they present here to translate our super operator approach to the arrow calculus. And so we can have a quantum programming language using this simple approach. And interestingly, there is these five laws can be used to do classical reasoning, to do quantum reasoning about programs. So in the same way as we do in traditional programming. And then we can extend this transactional method. Thank you.
Thank you very much. So, by the way, this was the Franciscan University Center in Santa Maria, Brazil. Sorry, the acronym quite right. Any time for maybe one quick question?